In chapter 12, electricity, we learned about the heating effect of electric current. What if I say you electric current carrying conductor or a wire behaves like a magnet? Isn't it interesting? Come on students, let's know what's happening. Now let us know that this is the instrument called compass needle or a magnetic needle. This needle deflects whenever it experiences a magnetic field. Let us have a look of a circuit in which the conductor is passing vertically, that is 90 degree to the board placed. That means the conductor must pass through the cardboard. On that board, a compass needle is placed. When we pass the current through the conductor, we observe that the needle is deflected. We know that the needle is deflected whenever the needle is experiencing a magnetic field. So from this, we can say that the electric current through the wire has produced a magnetic effect. This was accidentally discovered by Hans Christian Ørsted when a compass needle got deflected when an electric current passed through a metallic wire placed nearby. He came to know that electricity and magnetism were related phenomena. The magnetic field strength is named the Ørsted in his honor. Let us see magnetic field and field lines. This is a bar magnet similar to the needle. By placing the bar magnet on a cardboard and sprinkling some iron fillings around the bar magnet, we see that the iron fillings arrange in some pattern like this. This pattern is formed due to magnet exerts its influence in the region surrounding it. The pattern formed are nothing but the imaginary magnetic field lines. The field lines around the magnets are not visible but are present. This field line we can also discover by placing compass needle around the magnet and tracing the needle's direction, and then changing the place of the needle and so on. After doing this, we find the field lines around bar magnet as this. This field line starts from north pole of a magnet to the south pole of it. If the field lines are closer to each other, then the field of the magnet is stronger, and we must consider it as a strong magnet. No two field lines will cross each other. You must remember that. Magnetic field due to current carrying conductor. Now let us know the effect of current carrying conductor on magnetic field. By placing the compass needle below the conductor and passing the conductor from positive to negative, we observe that the needle deflects towards the east. If the direction of the current is reversed, the needle deflects towards the west. Let us now learn the magnetic field due to a current through a straight conductor. If a circuit as shown is formed where the conductor is placed through the cardboard with a variable resistance, that is the resistance which we can vary accordingly. Let the current flow through the circuit and sprinkle some iron fillings on the cardboard. After some while, we observe that the iron fillings align themselves, showing a pattern of concentric circles around the copper wires. These concentric circles represent the magnetic fields of line present around the conductor. Along with this, if we place the compass needle on the cardboard near the conductor, it deflects more. If we go on moving the conductor far from the needle, or if we move the needle far from the conductor, the deflection of the needle decreases. Similarly, if we place the needle near the conductor and keep it as it is and increase the current using variable resistance, the deflection of needle is more. If we decrease the current flow with that variable resistance, the deflection of needle is less comparatively. Let us now see the way of finding the direction of magnetic field associated with the current carrying conductor. That is right hand thumb rule. When we hold current carrying conductor in your right hand with fingers wrapped around, where thumb point towards the direction of current as shown. So the fingers wrapping around indicates the magnetic field and the thumb shows the direction of current. We saw magnetic field lines produced around a current carrying straight wire. Now let's see magnetic field due to current through a circular loop. In the circular loop, the concentric circles at every point represents magnetic field. If we move away from the wire towards the center, if there is a loop, it has a center. So if we move away from the wire that is arc towards the center of the loop, this field lines becomes bigger circles. The field lines will formed in a bigger circle, and the arc of this bigger circle appears as a straight line in the center of the loop. By increasing the turns of this circular loop, the field due to each loop adds up. If we increase the turns of the loop, then the field due to each loop adds up to become a stronger magnetic field, as shown in the figure. As we said, the addition of loop, we increase the turns, that is the addition of loop. The circular turns wrapped closely in the shape of cylinder, which we added the loops, or the circular turns which we added closely in a shape of cylinder. This is nothing but a solenoid. This is the pattern of magnetic field around a current carrying solenoid. Now look at the fields of this solenoid and the fields of the bar magnet. Aren't they same? Yes, they are similar to each other. By this we say that solenoid behaves as a bar magnet. By passing a magnetic material like iron through this solenoid, the material can be magnetized, and it also acts like a magnet. If we pass a iron or something through this solenoid, it gets magnetized and it behaves like a magnet. This is nothing but an electromagnet. What we call to this is an electromagnet. Now let us see what is the force on a current carrying conductor in a magnetic field. What is the force? Let us see. We learned that electric current flowing through a conductor produces a magnetic field. Similarly, magnetic field must also exert an equal and opposite force on the current carrying conductor. By this experiment, it can be demonstrated, which is shown. The rod AB in the figure is placed between the magnet and the current is passed from B to A. Of the bar moves inside the magnet, and if we pass the current from A to B, similarly in the reverse direction, this bar moves outside the magnet. This shows that the force is exerted on current carrying rod when it is placed in the magnetic field. Now it is placed in the magnetic field. When you start flowing the conductor, when you start flowing the current, the bar moves inside the magnet or it moves outside the magnet as we change the direction of the current. So when the magnetic field is reversed, now let us reverse the magnetic field. The force on the aluminum rod, this will also get reversed. By this we come to know that the force on the conductor depends upon the direction of current and direction of magnetic field. In this experiment, if the angle between magnetic field and current is at 90 degree, that if the magnetic field and currents are vertical to each other, then the force will be maximum on the conductor. There is a simple rule to find the direction of force on the conductor, that is Fleming's left hand rule as shown. According to the rule, stretch the thumb, the middle finger and the forefinger of your left hand in such a way that all are mutually perpendicular. If the forefinger indicates field, the middle finger indicates the current. Then the thumb will be indicating the motion of the conductor or the force what we talked acting on the conductor. Electric motors, generators, loudspeakers, microphones and measuring instruments like ammeter, etc. uses current carrying conductor and magnetic fields in them. So now let us see how an electric motor works. An electric motor is a rotating device that converts electric energy into mechanical energy. Electric motor is an important component of electric fans, refrigerator, mixers, washing machines, etc. Let us consider this diagram in which ABCD is a rectangular coil of an insulated copper wire which is placed between two poles of magnetic field such as AB and CD are perpendicular to the direction of magnetic field. These ends of the coil are connected to the halves P and Q of a split rings. These are the split rings. The half, this is indicated by P and this is indicated by Q. These are extended with a point X and Y and are insulated and attached on the axle. This is the axle. Now the current is passed through the point X. It flows through AB and return back from CD to the negative of the battery. By applying Fleming's left hand rule on this diagram, we see that the middle finger shows the current passing through AB and the forefinger shows the field between two magnets. Then the thumb shows downward direction. If we apply it correctly, it means the AB will goes down and coil CD rises up. As these are on the axle, they start rotating. For half rotation at point P, brush X makes contact whereas Q with brush Y. For the next half rotation, P gets contact with brush Y and the Q with the brush X. Now the current flows from DC BA of the coil. The commutators. These are the device which helps in flowing the current in reverse direction. As there is a reverse of current flow, force on the conductor also reverses. Where earlier it pushed down, the coil AB now pushes up according to the Fleming law. This continuously starts rotation of the coil and the axle. So this is the way how the electric motor works. In the commercial motors, the electromagnet is used in the place of this magnet. In place of coil ABCD, the large number of turns of conducting wire is used. These are in the commercial motors. The coils and soft iron core on which the coil is wounded is known as armature, which will be placed all together. A motor is prepared. Let us now discuss about the electromagnetic induction. We saw current carrying conductor was placed in the field which experiences a force in the electric motor. What if a conductor is moved inside a magnetic field, or magnetic field is changing around a fixed conductor? This important discovery was made by a great English physicist, Michael Faraday, from which he said that moving magnets can generate electric currents. Now he found that we can generate electricity or electric current through the moving magnets. Let us know what the effect is. So this device is known as a galvanometer. The work of this device is to detect the current in the circuit. The pointers of this device move to and fro according to the direction of the current and remains at 0 if there is no current. Now here is a coil AB with large number of turns and a galvanometer attached to the coil. When the bar magnet is moved to the north face, when a bar magnet is moved with a north face inside the coil, the galvanometer deflects, let us say in a right direction, which means it induced current. When the magnet is taken away from the coil, the galvanometer stays at 0. Now if the direction of the magnet is reversed, let us take south into the coil. The galvanometer deflects in the other direction, that is left. From this we get to know that there is an induced potential difference which set an induced electric current in the circuit. Let us now see this experiment in which magnet is replaced by another current carrying coil as in the figure. Let us consider this coil as coil 1 and coil 2. When a battery is connected to coil 1, the magnetic field changes, the electric current is induced. From this magnetic field lines around secondary coil will also change. Hence, secondary coil induces electric current in the galvanometer. Now what we did is we replaced a bar magnet with another coil, that is coil 1. When the magnetic field, when we start passing the current in coil 1, the magnetic field is changed. And when the magnetic field is changed, it is induced in the coil 2. So when the coil 2 induces magnetic field and generates current, the galvanometer, what does it? Deflects and returns to 0 immediately. Now let us disconnect the battery. After disconnecting, we observe that the galvanometer deflects in the other direction. From this we can say that potential difference is induced in coil 2 whenever current in the coil 1 is changing. We changed the current, we turned it on and turned it off, then the galvanometer start deflecting and remained at 0. As the current in first coil changes, magnetic field associated with the coil also changes. The induced current is found to be the highest when the direction of motion of coil is at right angles. So when the direction of motion of coil is right angle to the magnetic field, the current is highest. For this, a simple rule is used to know the direction of induced current, that is Fleming's right hand rule. In this right hand rule, the forefinger indicates the direction of magnetic field and the thumb shows the direction of motion of the conductor, and then the middle finger shows the direction of induced current. So this is Fleming's right hand rule. This Fleming's right hand rule explains the working of the electric generator. So now this completes your chapter 13, magnetic effects of electric current. Read the lesson carefully. If any doubts, ask in the comment section. Thank you.